Every architecture in this arc so far has been about proving who a human is. Here's the question none of them answer. Once a request actually reaches a service, how does that service know which other service is calling it, and not some process merely pretending to be it? For most organizations, the honest answer is still an IP address or membership in the right subnet. And neither of those was ever actually an identity. An IP address is assigned by a scheduler, reused by the next container that starts on the same node an hour later, and trivially spoofed by anything already sitting inside the network. Kestrel's original breach didn't need to defeat any of this, because nothing here needed defeating. The scheduling service and the billing service simply lived in the same VPC, and that was treated as identity enough. This episode is about the framework built specifically to replace that assumption with something a workload can actually prove cryptographically, the same way Zero Trust already replaced it for people. NIST 800-207 spelled out, a few episodes back, why a human's location on the network was never a legitimate basis for trust. The same argument applies to a workload with even more force, because a workload's network identity is even less stable than a human's ever was. An IP address is handed out by a DHCP server or a container scheduler, and it is explicitly designed to be reassigned. The same address that belonged to one pod an hour ago can belong to an entirely different pod, running entirely different code, the moment the first one is rescheduled. A firewall rule written to trust traffic from a specific subnet doesn't trust a specific service at all. It trusts whatever happens to be running at that address right now, which is a decision made by an orchestrator's scheduling algorithm, not by anyone thinking about security. It gets worse once spoofing and ephemerality compound each other. Inside a network segment where implicit trust already exists, nothing stops a compromised process from simply presenting the source address of a trusted service, because IP addresses were never designed to prove anything about the process using them. They're a routing detail, not a credential. And in an environment built on containers and autoscaling, the lifetime of any given address is measured in minutes, not months, which means any access control built around requests from a given IP range is really built around requests from whatever happened to be scheduled onto that range most recently, a fact that changes constantly and that almost nobody re-verifies once the rule is written. What was actually needed the whole time is the same property Zero Trust demands for people, translated into a form a piece of software can present, a cryptographically verifiable claim about who you are, checked on every single request, independent of where that request happens to be coming from on the network. That's the specific gap SPIFFE was written to close. SPIFFE stands for the Secure Production Identity Framework. For everyone, and the first thing worth being precise about is what SPIFFE actually is. A specification, not a product. It defines a standard identity document and a standard way of thinking about issuing it, so that any organization's tooling and any vendor's software can agree on what a workload identity actually looks like, instead of every platform inventing its own incompatible answer. The document SPIFFE defines is called an SVID, a SPIFFE verifiable identity document. An SVID is a cryptographically verifiable identity for exactly one workload, and it comes in two interchangeable encodings. An X.519 SVID is an X.519 certificate, the same certificate format mTLS already uses, with the workload's identity embedded directly in the certificate's subject alternative name field. A JWT SVID is a signed JSON Web Token carrying that same identity, useful anywhere a full mTLS handshake isn't practical, behind a proxy, for instance, or across a hop that only forwards a bearer token. Same identity, two formats, chosen based on what the calling context can actually carry. That identity itself is expressed in a specific, standardized shape. A URI in the form SPIFFE://, then a trust domain, then a path, SPIFFE, Kestrel .internal/billing/service, as a concrete example. The trust domain names the security domain, issuing the identity, and the path names the specific workload within it. It's deliberately simple, on purpose, because the entire value of the format is that any system, anywhere, can parse it and know exactly what it's looking at, without needing to understand whatever internal naming convention produced it. SPIFFE is the specification, SPIRE, the SPIFFE. Runtime environment is the reference open source implementation that actually issues and delivers these identities in a running system, and it does it through a sequence worth walking through step by step, because the mechanism is the entire point. SPIRE runs as a server and a set of agents, one agent per node. Before an agent can issue anything to the workloads running on its node, it has to prove its own identity to the server. That's node attestation, and it works by having the agent present runtime evidence about the node itself, a cloud provider's instance identity document, or a Kubernetes projected service account token, something the server can independently verify against the actual infrastructure, rather than simply trusting a certificate baked in at build time. Once the server accepts that evidence, the node itself is trusted. Workload attestation happens next, and this is the step that actually replaces the IP address. When a workload on that node asks for its identity, the SPIRE agent doesn't ask the workload to present a credential at all. It inspects runtime evidence about the workload directly, which Kubernetes service account it's running under, which pod and namespace it belongs to, which Unix user or process attributes it has, depending on the platform. That evidence gets matched against registration entries the server already holds, and only then does the agent issue the matching SVID. The workload receives that SVID through the Workload API, a local API SPIRE, exposes on the node, typically over a Unix domain socket, so that a workload never has to embed a static, long-lived credential inside its own container image at all. It asks the local agent who it is, proves it's actually the process it claims to be through the same attestation evidence, and receives a short-lived, cryptographically signed answer, rotated automatically long before it could ever expire into a stale, dangerous credential sitting in a config file somewhere. Every SPIFFE ID names a trust domain, the security domain whose SPIRE server is the authority for identities issued under it. Typically, one cluster, one cloud account, or one clearly owned administrative boundary. Inside a single trust domain, this is a solved problem. One server, one root of trust, every workload underneath it gets an SVID rooted in the same authority. Real estates rarely stay that simple. A multi-cluster deployment, a multi-cloud footprint, or two organizations integrating their systems after a partnership all produce more than one trust domain that legitimately need to verify each other's workloads. SPIFFE's answer to that is federation, and the important design decision is what it deliberately doesn't do. It doesn't merge the two trust domains into one, and it doesn't require either side to hand over administrative control of its own identity authority. Instead, two trust domains exchange trust bundles. The public key material each side needs to verify SVIDs issued by the other. And once that exchange is in place, a workload in one trust domain can present its SVID to a workload in the completely separate trust domain and be verified without either side's SPIRE server ever having authority over the other's workloads. That distinction matters architecturally. A workload in the cluster, running Kestrel's own services, could trust an SVID issued to a workload running inside a hospital system partner's own infrastructure, verified against that partner's own trust bundle, without Kestrel's SPIRE server needing to know anything about how that partner runs its nodes internally. Each side keeps full ownership of its own identities. Federation just gives both sides a way to verify the other's claims without collapsing the boundary between them. Kestrel's post-breach architecture review, done properly this time rather than under incident pressure, went back and asked the specific question this whole arc keeps returning to. What actually let that attacker move from the scheduling service to the billing service once they were inside? The honest answer, on paper, was almost embarrassingly simple. Both services lived in the same VPC. The billing service's access rules trusted traffic from that VPC's address range, full stop, with nothing checking which specific service was actually making a given call. Once the attacker's foothold could reach that network segment at all, it was, as far as billing was concerned, indistinguishable from the scheduling service it was impersonating. Deploying SPIRE across that environment closes exactly that gap, not by adding another network rule, but by removing network position from the trust decision entirely. Every workload, scheduling service included, billing service included, gets a SPIRE agent on its node performing workload attestation against its actual Kubernetes service account and pod identity, and receives an X.509 SVID naming it specifically SPIFFE.Kestrel.internal/scheduling/service, SPIFFE Kestrel.internal/billing/service, two entirely distinct, cryptographically distinguishable identities. Billing's access policy no longer asks which subnet a request came from. It asks which SPIFFE ID is presented in the calling certificate, and it only accepts the one specific identity it's actually supposed to receive calls from. Run the original attack against that architecture, and the failure mode simply isn't available anymore. A compromised process on the scheduling services node doesn't inherit scheduling's identity by merely living near it on the network. It would have to defeat workload attestation itself, forging evidence about its own service account and pod attributes that SPIRE's agent independently checks against the Kubernetes control plane. A fundamentally harder problem than simply reaching the right subnet ever was. It's worth being explicit about what actually makes this practical at runtime. Because the SVID isn't a separate credential living alongside mTLS, for the X509 encoding, it is the mTLS certificate. When two workloads establish a mutually authenticated TLS connection, each side presents its X.509 SVID as its client or server certificate, and each side validates the other's SPIFFE ID against its own policy. The same handshake mTLS already performs, just backed by an identity attested to the actual workload rather than issued once and left to go stale. SPIRE rotates those short-lived certificates automatically, well before expiry, exactly the operational discipline machine identity at scale demands, and exactly what a later episode this season on certificate lifecycle across an mTLS estate is built to cover in depth. It's also why service mesh platforms lean on SPIFFE rather than inventing their own identity model. Istio, covered later in this season, issues workload certificates that are SPIFFE compatible by design, which lets a mesh's own enforcement layer and a separately run SPIRE deployment describe the same workload the same way, rather than maintaining two incompatible identity systems for one problem. Both SPIFFE and SPIRE are real, actively maintained projects under the Cloud Native Computing Foundation at graduated status, the Foundation's highest maturity tier, reserved for projects it considers stable and production-proven at scale. That matters here specifically because it isn't a single vendor's proprietary format an organization would be locking into. It's a community-governed specification with more than one interoperable implementation, which is exactly the property that made federation across organizational boundaries workable in the first place. Where architects most often get this wrong, treating a SPIRE rollout as a one-time deployment rather than an ongoing attestation practice, letting registration entries drift until workloads start failing to fetch identities during an incident, and skipping federation planning until the second cluster or the first partner integration is already underway, at which point retrofitting trust bundles across an estate never designed for more than one trust domain is far more disruptive than planning for it from the start. SPIFFE and SPIRE answer how a service proves who it is to another service, continuously, without a login screen and without a static secret sitting in a config file. There's still one identity problem this arc hasn't touched at all: how a human proves who they are in a way that can't be phished, because everything covered so far in this arc, SAML, OIDC, even a well-run federation gateway, still assumes a password or a one-time code can be entered somewhere, and both of those can be stolen. That's FIDO2 and WebAuthn, phishing-resistant authentication by design. That's next episode. If you're building systems where identity has to survive contact with an attacker who already has a password, not just one who doesn't, subscribe, and I'll see you in the next one.